Swayam Prabha. Digital India. Educated India.
So we have been we have been discussing. So we have been discussing um, basic BJT amplifiers. Okay, and let me just, it is not recognizing. So we have been discussing BJT amplifiers. Okay, couple of things we have discussed in the last class. Let me recapitulate about the properties of amplifier. We said that um, linearity is very important. Okay, so this linearity will be assured. We mention if we keep the BJT in the forward active mode. Okay, so that means VCB reverse bias and VB forward bias. Okay, and we also said that what linearity will ensure that we can use superposition principle. Okay, that means we can separately find out the could you please all mute your microphone? Please mute your microphone. Okay, so we can then separately see the effect of DC and AC signal on the circuit, or see the performance of the circuit in presence of DC and AC signal. Okay, and what this linearity also will do, it will amplify the all the input frequency equal amount. Okay, so this is what we mentioned already. All the input frequency present will be, it will amplify in equal amount. Okay, so linearity is very important, and linearity will be ensured if we keep the BJT in the forward active mode, because we have seen the transfer characteristics, and we have seen that in transfer characteristics the V out, that is VCE, is proportional to VBE. Okay, that is what we have seen, right? So we also mentioned that when we see the performance of a circuit in presence of AC signal, we can remove all the DC signals, or DC signal as it is not changing. What we can do, all the supply voltages, okay, can be replaced by short, right, and all the supply currents, okay, can be replaced by open circuit, because we are assuming that we are assuming that, or we have also shown in the last class that we can for AC signal analysis, we can we don't have to take into account this effect of DC voltages, although it is implicit that when we will use we will see the effect of AC signal, the BJT should be in the forward active mode. So BJT will be biased in forward active mode, but we can see the effect of AC separately compared to that of DC voltages, DC signal. Okay. So one of the microphone is on. Could you please all mute all the microphones?
You can mute him.
Yeah. Now, to analyze the effect of AC signal on the circuit, what we will do now, we will find out the some AC parameters or small signal equivalent circuit parameters. Okay. So let's if we just consider BJT is just a two-port network where we have this is our IB and this is our VBE. Okay. This is our VCE and this is our IC. So all are AC signals and we are considering BJT as a two-port network. Okay. Let's define some of the small signal parameters. If we look at from the input side, you remember we have so this total instantaneous base emitter current varies with total instantaneous base emitter voltage exponentially, and we can take the slope at Q point. Okay. And from the slope we can get the input resistance or we say diffusion resistance. Okay, this is we have discussed before or we have come across before. Diffusion resistance usually denote as R pi. Okay. This R pi can be so this is at Q point. Okay. So if you so this 1 by Vt will come out. Okay. So that's basically sorry. So this diffusion resistance can be written as like this. So you should remember that if we increase ICQ, okay, this diffusion resistance will decrease. Okay. later on we will see that this diffusion resistance is nothing but the input resistance of the amplifier. Okay, sorry, input resistance of the amplifier, that we will see later on. Okay, and so this parameter is very important, and you see that this will decrease if we increase ICQ, right? Now that we will see that we will discuss later on, what is input resistance or input impedance of the amplifier. So this is one parameter, one small signal parameter. What are the others? The other one is, we know that collector current basically depends on exponential VB over VT, right? So that depends on exponential VB over VT. So if we try to establish the relation, try to exploit that relation and find out the small signal model or small signal parameter between this VBE and the collector current IC, so that can be written like this. And we know IC equal to IS T. So you just use that, and if we do del IC del VBE at Q point, we will ultimately end up with this is basically ICQ over VT. Okay, this is known as GM. So we have already know R pi. This is often known as GM. This is transconductance. This is called transconductance. Okay, because this is basically relating collector current, change in collector current with respect to change in base emitter voltage. So that is basically transconductance, you see, because we are relating input with output. So that is transconductance. So here you again remember that if we increase our collector current, your GM is going to increase. Okay, you see that is opposite. If we increase our ICQ, you see, if we increase ICQ, that R pi is decreasing, whereas if we increase ICQ, your GM is going to increase. Okay, now the third parameter we would like to find out is basically we know that is del IC by del B. Okay, at Q point, that is basically beta. Okay, so we can relate these three parameters. Okay, we can relate these three parameters, and often we will use this particular relation, because you see R pi is equal to beta VT over ICQ, and this is GM is ICQ over VT. So that's basically giving you beta. Okay, Now there is another parameter which is R naught, that we will discuss. We can discuss later on, or I mean, in fact we can discuss now. This R naught is basically coming because of the early effect, okay, that we have discussed elaborately before. Okay, that is basically del IC over del VCE at Q point, and if you put those IC value, of course here you have to consider one additional term. You have to consider one additional term as because the early voltage is coming into picture, so this is the additional term, okay, and this is this early voltage, and if you take the derivative of this IC with respect to del VC at Q point, you ultimately get R naught equal to VA over ICQ. Okay, this is also this relationship we have discussed before. So these are the four small signal parameters which we will use to replace our BJT when we will discuss the small signals. So if I draw this is my R pi, okay, and this is GM V pi, okay. If I consider the voltage drop here is V pi across R pi, so that is GM V pi, because V pi is basically, you can say, V is VBE, okay, and this is basically your R naught, okay. So these are the small signal parameters which we will use to replace a BJT circuit when we will analyze the BJT as a amplifier, right? Now couple of one important thing I forgot to mention in the last class, that is input output impedance of any amplifier, okay. This input output impedance of any amplifier is very important, because what we do, we say this is my amplifier block, okay. This amplifier block will be interfaced with a system, okay, whose signal we are going to amplify, okay. So there will be a input system whose signal we will basically amplify, okay, and it will be delivered to a load, right? So the input output impedance of the amplifier is very, very important. How it is important? We can intuitively think or intuitively guess what should or what kind of input output impedance the amplifier should possess, okay. As it is a voltage amplifier we are discussing, so then the input impedance ideally should be infinite, okay, because otherwise it will load your system which it is interfacing, okay. What about the output impedance? The output impedance of this amplifier should be 0. In other words, this kind of voltage amplifier acts as a voltmeter as far as the input signal is concerned, whereas it is acting as a as a voltage source, okay, for the output load, right? It will be more clearer if we take an example. For example, say I have a microphone, okay, whose signal I would like to amplify, and this microphone amplified signal is going to a speaker. Okay, what I am trying to tell you is about this input, and through this example is about the nature of input and output impedance an amplifier should possess. Let's say that the gain of the amplifier is 10, okay, and let's assume that that the peak to peak signal of the amplifier of the microphone is 10 millivolt, okay, and let's assume that the microphone has a series resistance of 200 ohm, right? Now if I have if I take some values, for example, say R in of this amplifier is 2 kilo ohm, okay, so if it is 2 kilo ohm, so the voltage you will get at the input of the amplifier, okay, say this is my Vs and this is my V in of the amplifier, okay, so V in will be equal to right, so that's around 0.91. So you see the amplifier, there is around 9% loss of signal, okay, when it is coming to the amplifier. In other words, if I have, instead of 2 kilo ohm, if I have infinite resistance at the input of the amplifier, you will get the entire Vs at the input of the amplifier, so that it can amplify that, okay. Similarly, if I assume that this speaker has a resistance of say 8 ohm, okay, and let's assume that the R out of this amplifier is 2 ohm, okay, so you see the V out we will get, you can similarly write V out we will get is V amplified, okay, multiplied by 8, 2 plus 8, okay, right, so that's around 0.8 V amp, right. So if I consider V amp is the amplified voltage coming from amplifier, so you see you are losing 20% of the signal. If you have like R out of the amplifier close to 0, then you get entire amplified signal at the output, that is at the speaker, okay. In other words, as I said, like the input impedance of the amplifier will be as large as possible, okay, so that it shouldn't load the input which it is interfacing, whereas the output impedance should be as small as possible, so that it can deliver the entire amplified signal to the load, okay. Now how we can find out this input and output impedance, that we should understand, although I will cover that very briefly. Okay, how we can find out this input and output impedance. The way we usually find out input and output impedance, say this is my amplifier. Okay, for finding input impedance, we have to apply a test voltage Vx. Okay, and we will measure the corresponding Ix, which is entering to the amplifier. Okay, and of course amplifier output is open circuit, right? What about, so this is for finding input impedance of the amplifier. What about output impedance? When we try to find output impedance, so we are looking this direction here. When we find output impedance of the amplifier, we again connect a test voltage at the output, and we will measure what is the current entering through this output port. Okay, so this is your output port, and this is your input port, right? Remember, you have to short this input signal. Okay, you have to short because you are measuring. So this is same like the thing you adopt when you have, like, you calculate Thevenin impedance of a circuit, right? So when you remember, when we calculate Thevenin impedance of a circuit, we because there is no output signal we are applying, so we open circuit the load, we open the load and put a test voltage and measure the current. So this Vx over Ix will give you input impedance. Similarly, when we try to find out output impedance, we need to connect a voltage source, test voltage source Vx at the output, and we find out Vx over Ix, that is the current which is entering at the output. When we have shorted the inputs, I mean the voltage present at the input, because we usually put small signal voltage at the input, right, for the amplifier. So we need to short that voltage signal. Whereas when we are finding the input impedance, there is no voltage signal at the output, we are not applying any voltage signal, so we have to have like open circuit at the output. So this is the same thing you remember, probably you have come across before, when we have like Thevenin impedance calculation, okay, for a circuit. Now we can use this approach and find out the input and output impedance of our BJT amplifier. Okay, how we can do that? Let's see. This is our BJT amplifier. Okay, right? So we can replace this with a small signal model, that is, we have R pi here, we have corresponding GM V pi, okay, because there is voltage drop V pi here, and we have R naught here. Okay, this is grounded. This RC also needs to be grounded, because you see for this AC signal analysis we short all these DC voltages, so RC is basically AC ground. Okay, so if we want to measure, if we want to find out the input impedance, what I have to do, we have to connect here Vx and Ix. Okay, so this will be your Ix, okay, and this will be your Vx. Okay, so this Vx over Ix will be your R pi. Okay, that's basically your input impedance. You remember we have mentioned just few minutes ago that let me go back. Sorry, how to go back? So you see, I wrote it down here. Input resistance or input impedance is basically R pi. Okay, so that is what I have written again. So R pi is your input impedance. Okay, you see, we know R pi equal to beta over Gm, right, or beta Vt over Ic, and as I said to you before that higher beta or lower Ic, okay, will give you higher input impedance. As I said, higher input impedance is important. If we have lower the Ic value, our input impedance of the amplifier will increase. Okay, what about the output impedance of that circuit? Okay, so if I want to find out output impedance, we need to ground the input side. Okay, of course you can I'm just not taking into account RC. You can take RC into account. That will be then R naught parallel. So here you see, I'm coming to that in a minute. So here you see V pi is equal to 0, because you see V pi is basically shorted here. Here it is grounded and here it is grounded also, right? So R pi is shorted means this V pi is shorted. So this Gm V pi we can is no longer be there. So this R out, if you look from this side, output port, R out will be equal to R naught. Okay, or you can write R out will be equal to R naught parallel RC if you consider RC. Okay, now what about the input impedance if we look from emitter side? Okay, there might be a situation where you need to look input impedance from emitter side. So I'm just ignoring RC for the time being. Okay, so this is my Vin, this is VCC. What I am interested in to see the resistance or impedance if we look from emitter side. Okay, then again we replace R pi. I mean, we replace V in with, we need to ground V in. Okay, we need to ground. So this is our Gm V pi. Okay, we need to ground that because VCC is grounded. I'm just for the time being not considering RC. Okay, and here what I have done, I have used a Ix and Vx to see what is the resistance from this port, from the emitter port. Okay, so this is our V pi. So if you see carefully, the two currents, current is basically two currents are here. Okay, two currents are here, and there is one current Ix. Okay, so we can write one current GM V pi plus the other one V pi over I pi, sorry, V pi over R pi, okay, equal to your minus Ix, okay, equal to your, because Ix direction and these two current direction is opposite, you see. So if you look carefully, this point, say the point, this point here, okay, say this point is X, okay, this X, this point here, if you look carefully, this V pi and Vx is basically in parallel, you see. So in other words, V pi is equal to basically Vx minus Vx, okay. If you see carefully, I think this is understandable. This is grounded and also this is grounded, so this point, these two are like parallelly connected, so this V pi is effectively minus Vx, okay. So if you use that, you will end up with, Vx over Ix is equal to 1 by Gm plus 1 over R pi, okay. So that will ultimately give you, because you remember R pi equal to beta over Gm, okay. So we can neglect, so we can write 1 by Gm plus Gm over beta, okay. So we can neglect this second term because beta is couple of hundred usually, so we can write these as uh, 1 over Gm. So this point you should remember very carefully. Let me write it down once more. So if we look, because you have to use this in many in future in many circuits. If you look from, so let me summarize. If we look from base side, when the emitter is grounded, we will get, we will see the impedance as R pi, okay. If we ground our emitter, okay, if we look from collector side, okay, and these two are grounded, these are all AC ground, okay, these two are grounded, these are all AC ground, right. So you ground, if you ground both base and emitter, you will see the output, you will see this resistance at R0, okay. What about here? Here if we have like if we see our see the circuit, see the BJT from emitter side, okay, we will get 1 by Gm. So you remember this point, this you have to use many a times for any circuit analysis, and you should remember these values, that when we look from base side, the input impedance is R pi. When we look from collector side, the corresponding impedance is R0. Of course, the emitter is grounded, AC ground, and when we look from emitter side, of course, here we have to consider that the early voltage is infinite, or there is no early effect, okay. Then it will be 1 by Gm, okay. You should remember all these three cases. Now the last point I would like to mention today before we close this session is these amplifier topologies. We can have many different configurations, okay. For example, as BJT is a 3-terminal device, okay, you see we can connect, so we can get different amplifier topologies. For example, we can connect our AC signal to base, we can connect AC signal to emitter. Okay, we can connect AC signal to our collector. Okay, these are whatever input is concerned. So these are all inputs I am talking about. Okay, input connections, possible input connections. What about possible output connections? Possible output connections, maybe I can have like V out at the collector. Okay, I can have like V out at the emitter. Okay, I can have like V out at the base. Okay, so these are possible output output connections. Okay, now if we think carefully that in case of bipolar transistor, the bipolar transistor operating in the active mode, okay, the base emitter voltage variations by varying the collector current. We basically see the base emitter voltage variations, and that basically reflects at the collector current. Okay, thus if we follow this rule, okay, then you see that this particular topology will not we will not consider this. Okay, because we are saying that we are taking V out from this from base. Okay, so this particular topology will not consider. What about the topology here? This will also we will not consider, because here we are connecting input at the collector. Okay, so these two topologies doesn't make any sense. So instead of 9 combinations, okay, 3 into 3, out of these 9 combinations, we will have only 4 combinations. Okay, we will have only 4 combinations. What about what about the combination here? Okay, this particular combination doesn't also make any sense. Okay, because here you see we are applying input signal as emitter, and we also look the output at the emitter. Okay, then so this combination also, it doesn't make any sense. So we will have 3, in a nutshell, we will have 3 combinations. Okay, we will have 3 combinations where we will give input here at the base. We will see output either collector or emitter. Okay, so that will give us 3 combinations, and we will see whether we can cover all these 3 combinations in this class, but we will definitely discuss this particular approach, this particular combination in the class. Okay, now so what we will do in the next class, we will start our discussion with the simple CE amplifier circuit. Okay, in the first case we will take only BJT. Okay, so we will see how the small signal equivalent circuit, using the small signal equivalent circuit, what kind of gain we are getting when we apply an input signal. Okay, so we will basically have the simplest amplifier circuit. Okay, we will not for the time being we will not bother about the uh, about the biasing circuit, that we will consider later. Okay, and we will find out V out over V in and see how much will be the gain out of this simple amplifier circuit. Okay, you see, if you increase V in by delta V, okay, your current is also going to increase GM delta V, right? GM delta V. So that's the collector current is going to increase. Okay, so the corresponding collector corresponding voltage will increase, is multiplied the resistance RC will be the corresponding increase in voltage, and so on. So we can relate V out and V in and find out the expression of the gain. Okay, and we will see how gain is related with GM and with beta or with R pi and so on. Okay, and from there we will have some interesting conclusion to make, like how this although we are not we don't consider VCC, this capital VCC, when we do this AC analysis, but we will see that capital VCC has an important role to play, because VCC and RC will ensure the reverse bias of the VCB. Okay, and VCC and RC will tell you the how much headroom we will have. So VCC and RC will have an important role to play for this gain of the amplifier. So these things we will discuss in the next class. So with this I'm closing this session. So if you have any queries, please raise your hand and we can discuss.